So let's take an example. Let's look at an example of the radial probability for the 1s state. So what have we done here to calculate radial probability? We've taken psi squared. We've squared 1s wave function. And we've multiplied it by 4 pi r squared dr, right, for all these values of r. So we've calculated psi at all the values of r and multiplied it by 4 pi r squared dr. And the result is this radial probability. All right, that's what I'm plotting right here. What do you see? Well, the first thing you see is that the electron, the most probable value of r, or the most probable distance of the electron from the nucleus, is quite a ways out. That most probable value is all the way out here, where r is equal to a naught. And I said last time that this a naught is a constant. It's called the Bohr radius, and today I'll explain why it's called the Bohr radius. But it has a value of 0.529 angstroms. All right? So it's most likely to find the electron about a half an angstrom away from the nucleus. All right? The most probable value, or the most probable position of finding the electron, is not at the nucleus. And in fact, hey, look at this. In fact, that radial probability here is actually, let me focus my pointer, there you go, is actually 0 at r equals 0. Hey, that seems a little strange because we looked at the probability density. Remember, we plotted the probability density the last time, which was just psi squared for the 1, 0, 0 wave function as a function of r. And when we did that, we saw that at r equals 0 here, the probability density was some large maximum value, and that this exponentially decayed. Well, the probability density is a large maximum value at r equals 0, but when we look at the radial probability, it's 0 at r equals 0. Why? Well, because when we go to calculate the radial probability, we are multiplying that probability density by a sphere. A sphere whose volume now has shrunk to 0 because r is equal to 0. All right? So the probability of finding that electron right at the nucleus between r equals 0 and r plus dr is 0. All right? So the most likely distance of that electron in the hydrogen atom from the nucleus is 1 Bohr radius. And actually, then the diameter of that hydrogen atom, we typically say, is twice the Bohr radius, or a little bit over an angstrom.